Hello, everybody. Welcome to the discussion. My name is Kevin Kawchak. I'm the founder CEO of ChemicalQDevice. This is for how to create, optimize, and implement quantum machine learning algorithms. This is August 3rd, 2023, number 94. So I found a lot of good stuff, and I've been implementing into models, running all these notebooks kind of thing. And I'll share with you this first. Does anybody have any questions first off? So this is definitely for people that want to go further with quantum programming. Any questions? There's been a lot going on with events. So there's been Womanium that's, I believe, still going on. Qiskit Summer School, which is IBM. Really kind of fascinating. You can go into a lot of these forums and help them with their code, or you can ask questions yourself. So Qiskit, Penny Lane, they have these types of things. So I'm putting in the chat this first part here, assuming nobody had a question, is basically it's creating quantum algorithms in Qiskit, right? So there's many platforms of doing this. So I'm just going to stick with IBM Qiskit today. It tends to be more universal. It's a lot more customizable than some of the other ones. So that one, basically, you want to get to the point where we're running on notebooks. So these are in GitHub. So this first thing I put in the chat is it keeps taking me here. Okay, circuit basics. So if you're new to quantum computing or quantum machine learning, you want to understand what a superposition is, entanglement, interference, these types of things. Now, that particular one will help you get going, the circuit basics. So they have a specific example where they put a Hadamard gate in, and it adds a superposition, turned it into a Bell state with a CNOT gate, and then add another CNOT gate it's called a GHZ gate state. So GHZ has been in the news with Quantinium, and they were able to entangle 30 or more qubits in this high entanglement environment with ion-trapped quantum computers. So when you do these notebooks, a lot of times you want to think of it, you're not doing that much different than what these huge experiments are, because you can use simulators, okay? And I'll get to that a little bit later. So the second one I put in the chat is this introduction to algorithms. So TwoLocal is specific. I believe what it does is it does alternating gates, and you tell which two gates, and the IBM Qiskit does the rest. The SLSQP is an optimizer, and the specific application for that one is a molecule. So if you have any questions during this, feel free to unmute. You can also come on. I'd love to hear, and especially as we get through this first part, the progress that people are making with quantum machine learning, quantum computing. The next one I put in the chat are advanced circuits, and I thought this one was really cool because I didn't know that you could do this with Qiskit, custom gates, composite gates, and then up to parameterized quantum circuits or PQCs. So those are some features that I didn't think that you could do. Now, what's coming up in probably future discussions is pulse gates. So pulse gates is basically you can modify the qubit as it goes through this, your program, and then you can do additional fine tuning. And I got into a model, and I could see when I changed some of these parameters what it was doing to the Hadamard gate. So that's the one I'm talking about. It's called Qiskit pulse gates to check out. And then there's also Qiskit building pulse schedules, and this is getting really in depth with this. So I know a lot of you might not have heard of some of the more advanced things, but I'm kind of interested. Does anybody have any questions regarding their specific code that they're working on or the algorithms? And feel free. So I saw some people hop in here. So we could go David or Marcia. And then if not, I mean, that's fine if you're just learning. But I think with anything, it's just, it's definitely building. And I would say, with pulse programming and I'll get to Transpile, which is high level to high level, code, that you'll start to see this is where a bulk of a lot of the work is happening, especially with transpiling, because this is essentially what is being run by the quantum computer, as opposed to your circuit that you're designing in Composer, for instance, like those with those specific gates. And are any questions? Any questions? Especially regarding your code or these types of things. I do a fair amount of on Slacks. So I'll go on Qiskit Slack. I'll go on Ticket Slack. I'll go to Penny Lane discussion forums. Sometimes I'll have questions, and sometimes I can help other people. So these types of things, definitely helps to kind of be involved with the community. And I'd say those are some of those resources out there. Now, this next one is optimizing quantum algorithms. So you'll hear this term in quantum machine learning, especially optimizing algorithms. So what does this actually mean? It's famous, and Quantinuum says they have 3 steps. So you could set an optimization, say 0, 1, and 2, and it's effectively doing a stuff behind the scenes to reduce the number of gates that you have or make it run faster. And I would say the Qiskit is, they have 4 levels, 0, 1, and 0, 1, 2, 3. They're probably more customizable than some of the other options out there. So I put 2 links. The first one was cool because it told you the exact how things are transpiled, or in other words, taking your language and then having it so the machine can run it, is the first link. And then the second link is how to do this in notebooks. So there's configurations. So say, for instance, at the end, you would say comma space optimization equals 0, which is nothing, all the way up to 3, which is doing something significant to the circuit. And you could see the kind of the before and the after. So this is definitely, like I said, like watch basically these tutorials or these demos. There's a lot going into this fine tuning of something that you create that we can all reflect on, like Hadamard, C-Knot, certain entanglement patterns, and then now all of a sudden the computer is more efficient if it's transpiled this specific way. Are there any questions with this, with transpiling? So it's similar to compiling, but transpiling is typically high to high level language. Go ahead, Barry.
Kevin, are you doing any screen sharing? Because I'm not seeing anything.
Right. So everything's in the chat.
Okay.
And then I'll post the PDF afterwards. So you'll have that. And it's got all of the links to the notebooks, those types of things as well. So, yeah, these are the... if you ever have that question, like, can you do it? Like, the answer is usually yes with quantum computing or quantum machine learning, because it's either in a paper, it's in a tutorial. Like, so Qiskit calls them tutorials, and then say, for instance, Penny Lane calls them demos. Ticket has some, Google Circ has some, and kind of their offshoot is called TensorFlow Quantum. So yes, everything's available, the links and everything in the chat, and I'll post the PDF a little bit later as well. Now, any other questions regarding optimizing algorithms? So this is typically, that term optimizing circuits or optimizing algorithms is specifically usually used for, okay, you have this quantum algorithm, and then how can it, like, less number of gates or turning like, multiple, more into single qubit gates, like more X gates, those types of things. So the next thing is the crux of it. So if you know machine learning, so quantum machine learning is a similar approach. So in classical machine learning, you have, say, for instance, weights and biases in a deep learning neural network. Now on the quantum end, it's typically these days, it's those parameters are the rotations of the individual qubits. So then when you run, keep running data through, they get fine-tuned by the model if it's set up correctly. So in a form, we do have quantum machine learning already, because the end results of accuracy and loss are reflective of these parameters continuously being updated throughout the run. So if you have, like, you have batches up to epochs, and then epochs, and at the end of it, you're trying to get better accurate, that end metrics is due to the theta angles, or like the rotation angles on individual rotational gates like Rx, Ry, Rz. Are there any questions with that? Because there's a lot of hope with this, because it can go, they're talking about using coefficients in literature right now as an additional parameter. And then you can also do other parameters as well. Like, these things are not solidified. And I'm talking about parameterized quantum circuits. They're expected to get a lot better. The time where it replaces a full deep learning network will be a while, very likely, but there's a lot more that can go into, like, now you have coefficients you can update over the course run and on top of parameters. And there's all of these really awesome studies going on right now that, show promise as far as like, okay, this could significantly help it all. So in everything you have, I put a couple links in here. So consulting models and documentation. So this is in the chat. Inserting algorithms into models. Now, the part that's really important is if you're really good in deep learning, really good in machine learning, basically you're learning from a training set, you introduce unseen data, and now your unseen data has higher accuracy because the training set went well. That's the crux of machine learning. So you still have to do things like optimize hyperparameters. So model optimizer. So you could use stochastic gradient descent, which I've seen in a lot of classical models, and an atom optimizer, which is basically based on stochastic gradient descent or Adagrad. You loss functions, so binary cross entropy, and Gaussian NLL. So what these are doing is basically, just because you add a quantum algorithm doesn't fix all the problems. It's now a hybrid notebook. So a lot of it's classical code, and then you have this portion of quantum, and it's going to behave in a different way than your original classical notebook. So if you look at some of these models, like especially Penny Lane, is they'll go over this in detail. Or basically, I'll try other things besides what they already recommend. And a lot of times the original settings, like an atom optimizer, was the correct use instead of an SGD, like performance a lot better with atom. So this goes into activation functions, and keep in mind, like quantum and quantum computing and quantum machine learning, it's not going to be confined to just a parameterized quantum circuit. And in fact, there's many algorithms out there that already have quantum exponential speedups as the algorithm, just not looking at the external factors in the model. But once you start to consider the data being inputted and then the output or decode or, these types of things or measurement, these things are tending to bring down the speed of the quantum exponential speedup. So that's a big concern right now, is how can, using the model differently, using quantum data instead of classically to, basically get the speed. And there's other things such as weight decay, weight spread, learning rate is a big one. So these are common in classical models, still apply to hybrid models. Learning rate reduction, which is basically after a certain number of epochs gets reduced, batch size and epochs I kind of touched on a little bit. So I'm interested in kind of where people are coming from, because, some people say, oh yeah, this is awesome, I want to do it. How do I do it? It's a lot of just hard work. I wouldn't say that you're going to get awesome results because it's right away, because there's a lot to learn, but you could still be pretty effective, using Penny Lane models, using your own data set, and kind of like you're building off of basically the shoulders of giants, really. So I saw some people come in, so feel free to unmute or you can come on. So this is David or Lorraine.
David.
Yeah, go ahead, Dave.
Oh, I thought you asked if it was me.
Yeah. So, yeah, if you have any questions as far as like getting started with how to set up a circuit, I mean, this is a pretty good guide right here. And I'll put the PDF up here as well. I also did about six discussions that has like the whole, the walkthrough, and it's got Qiskit up on the screen, that type of stuff. So I'll put that in the chat. I'll also put this, their example code. So say, for instance, like something simple, like adding a timer to your notebook, finding the least busy of the quantum computers, displaying which real hardware is available over a certain number of qubits. And again, with Qiskit, I wouldn't say it's too complicated. It's just, there's so many options as far as what you want to do. It's very well thought out of, definitely as a platform, in my opinion. Anybody that we haven't heard from? So Luis or Ron? So yeah, I'll put this up in the chat here, and it's to this point, it does take a significant amount of work, but if you dedicate your time as far as like you learn something, you teach it, you learn, you teach, and that could be through forums. So there's Qiskit Slacks, there's all these types of things. I just got an award, last month for Penny Lane because I like going on and learning and helping people, and sometimes I'll have questions. So it's like part of the community basically, is you go on and help people, and then your studies get more complicated, is hopefully where you want to go. And that's another thing is basically I want to hear is like the goals that you have for your notebooks, or what you want to do with quantum computing, kind of the obstacles, if there's anything like that in the way, and then kind of where you see this going. Or if you have questions as far as to get along that path. So I put in the chat the PDF. So this, and if you're struggling with any of these steps, like optimizing your circuit, or, basically transpiling it in a certain way you want to, or reaching these other things like pulse programming, it'll definitely help you out, these the demos, the Qiskit demos. And feel free to put in the chat too. So if you don't want to come on right away. And so I see Aquila or John, go ahead if you have any questions. And then we also have Shams or anybody we haven't heard from, or David. If you'd like to share your progress.
We a silent meet tonight?
Go ahead, John.
Hi. Hey, everybody, how y'all doing? Haven't seen you for a while. So my question is, you won an award for Penny Lane, huh? That sounds like fun.
Yeah, they're like badges. They say you win this, it's like new user of the month,
That's a
so
great thing. I mean,
well, there was
shows your-
two of us, so, but that's what there, a lot of times I'll research their documentation, or their Penny Lane's documentation, and figure out, it'll say this is the only way that you could run this function, right? So they're trying to do all these fancy things, and I'll just put that one line, copy to the thing, and then I'll, sometimes they put examples, but say for instance, like an RY gate has its own page, right? And it's very similar to the RX. These are gates, quantum gates. So yeah, they're you basically study these things for your own good, and others too.
Oh no, you both the study and then you basically work on it. I agree with that. Spend your time wisely. Has it enlightened you? That's
Yeah,
Have you
I
been-
mean, it's a balance, because ultimately for me, because I've got the startup and I've got medical data, and a lot of times with quantum is you can't get to that next step unless you do other things. So watch a lot of experts in lectures or seminars online, read literature, those types of things. And it's just unfortunately that's how it works. Like a lot of times you just can't, if I want, say for instance, like a 10 qubit, which is like a qubit, but it's 10 dimensions. If I want to do, say for instance, on that one, they have a term for this. It's basically doing everything on a single wire. So a single wire classification. Data re-uploading is the term that's coined. So I'll watch other things. So quantum walks, and if anybody remembers Salvador Ivanegas and Draka, I rewatched his his slides. He did quantum walks, and then he also talks about quantum image processing. And the field is quite broad, so that's why you kind of have to like pick something. So if it's like medical images, what's the best we could do with that? So yeah, it's I would shoot after the experts. There's Maria Scholl that Xanadu Penny Lane, and then just a number of early papers. I did a study this week, a 2014 paper, Introduction to Quantum Machine Learning. And the paper that she did in 2022, 2023 is so much more advanced than the 2014. And say if there was like a handful of papers, QML papers in the early 2000s, now there's several a day. And I think that's actually in 21, so it might actually be more than that. But there's if you're looking to do something, the literature is usually there or the lectures are there. And a lot of times you'll just have to sit and learn other things you aren't wanting to learn that day, but then you'll use at a later time, I would say.
Yeah, well, it's like when I got into class, my concern was accuracy, narrow resolution, because so much unpredictability was flared about these things. You know, I figured, well, that's not so, because the narrow band of per bias in it, therefore the more accurate, then you can apply that. Then next year, increasing these, then you start looking at error rates as a collective, right? And as a collective, then you start to gauge your programs around the collective. Then essentially you start to figure out maybe groupings, you know. So when I started talking sequential multiprocessing, I said, you know where to split off your quantum program to the machine, and as opposed to keep the classical side. So it's all theory. I'm not really practicing it. I'm just starting to get back in. But to me, you basically still use the classical machine to define in certain terms, and you're also using the quantum machine to basically predict them.
Yeah, and I would say, and thanks for all that, is a lot of it's narrowing down for sure. As far as, so Lorraine put in the chat here, what area in quantum machine learning is already proven to be very useful, such that I could explore that area. And I would say the two things, there's already, and you can use quantum simulators for these, so to get better performance. So this is like better accuracy. We're not looking at speed, okay? This could be a new utility. So there's many applications that just quantum mechanics math is different than classical, and you can go these routes. And these two are typically not studied nearly as much as speed. So quantum speedups or quantum advantage, quantum supremacy, those are usually tied together. The algorithms, there's many, like if you look at Seth Lloyd's, presentations online, there's many that are exponential speedups, but the issue is getting it into a working model, because the data, if it's classical data into quantum data, and then the measurement at the end, if it goes into the output. So in other words, we have a lot of these algorithms that look awesome. It's just a matter of improving these other areas for fully functional models. Say if I have this awesome model, I want like PyTorch or Hugging Face. They actually just had an announcement this week. So I say, okay, I could do this with quantum machine learning where they don't know much about quantum at all, and it's better in accuracy, or it's something that you couldn't do classically. So those are the cases. So I just did a quantum transfer learning model, and I'm still kind of unpacking it. And the best thing I could do is basically compare it across like 15 or 20 other quantum algorithms. And that was good. But a lot of times the benchmarks are there to compare it directly to classical. Like there's good classical benchmarks. These are still developing. And I think you could look at the Maria Schuld 2022 paper on this. So that's a good place to start, I would say. And then feel free to come on if you had anything, David. So David says there's a quantum break from QGSS23 and Womanium, a break from Pennyland QHack too. So for those that are also wanting to get into specific areas, there's like probably close to 100 QHack videos between 2022 and 2023. This is Xanadu, like Penny Lane. And they have experts beyond, experts from all the leading companies. It's not just Penny Lane. So there's, IBM, there's Lanel. So Lanel's a leader at Los Alamos National Laboratory, and others to Google. So they'll summarize a paper in a presentation. So if you can't understand the paper, you have like an hour's worth of a presentation that might be more digestible. Yeah, so it's the type of thing like when you're in software, number one, you don't have to be huge. Like if you're designing hardware, you for sure have to have materials. So it's a kind of thing like as underdogs, basically, is you could come out some of these boot camps and keep going, not give up, and then implement the new literature, and then you might be in the race. So definitely it's a with software, it's like an equalizer. So I saw a couple of people. So Ron, if you had anything, or David.
So, looks like a couple of us in here have attempted the Wilmanium Summer School and the IBM Qiskit Summer School at the same time, which has been great because the downside of IBM is all you learn about is IBM, but in the Wilmanium, we did D-Wave, we did Penny Lane, we did the Xanadu stuff. We also were exposed to some neutral atom companies that are coming on really strong. I think one of the companies was called QEra. They are coming up with mechanisms whereby they can float the atoms around to really do some interesting QML and other type of problem solving stuff. So my question is of the big players that are currently out there, like Penny Lane or Xanadu, Penny Lane, the people over at Quantinium doing ticket. What's your experience as far as who's getting some real world work done at a reasonable scale?
Well, I mean, that answer is usually D-Wave, right? So D-Wave's been around since year 2000, actually, I think a little bit before that. They actually started in gate-based superconducting qubits, which is like IBM and Google and Rigetti, and they've been doing annealing. And they sold their first quantum annealer to Lockheed Martin some years ago, not too long ago. And on their website, they say 250 plus applications for it. So you get the qubits, right? You're limited to these, is it COA or Kubo, these types of algorithms that are annealing specific. And it's going to have some noise to it. So in a lot of these things we talk about, it's still considered R&D. So say, for instance, in medical, you're clinical, at some point with quantum. And the rubber hits the road. You have IonQ at Dell. So they said they're using an emulator. So it's basically an emulated, I believe, ion trap setup, or anyways, it's simulated. And, NSF still says practical quantum computer this year. So it'll be interesting to see what else comes out. I think the Quantinium announcement of getting closer to logical gates, because physical gates are like the QPU. They've made that announcement. They just made, was it 32 qubit GHZ states? That seems it's definitely going places. So, it's really, there's an IBM in Cleveland Clinic. They installed the first quantum computer in healthcare at Cleveland Clinic, and it's probably going to have to be updated, right? If it's gate-based superconducting qubit, but they're still doing research in the area, and I'm talking like more like simulators. So it just depends. It's really hard to prove the quantum advantage, or if you're doing the head-to-head benchmarking versus classical, because even though if I have two pretty similar models, they're still not exactly the same. So that area is getting better as well. So if there's medical image classification, there's been like 7 or 8 papers on this, and you compare it to previous deep learning neural networks and these types of things. But it's a lot of it's just has to get to the next generation, right? So it's like this for sure. You need to do it this way. Start with the algorithm, and then is it in the model? And then, how did you do this? And with benchmarking, those types of things.
So, what you just said begs a question, because I hear this come up a lot. Oh, we created a 32 qubit GHZ gate. Great. What the hell can you do with that? No answer.
Well, it's
And
interesting. Yeah,
and
go ahead.
the reason I think it's funny is because in the IBM Spring Challenge, one of the tasks you had to do was create 127 qubit GHZ state, and then once you created it, you had to tear it back down to 54 qubits, and it had to be the qubits that were of a particular color on the on IBM's interconnect grid map. But once again, great. Now I created a 127. I reduced it to 54. At 54, I had one shot at running it on the Eagle processor, and it came back a mess because the circuit depth was too much. But never got an answer to the question, what the hell good is that state? What do you do with it?
Yeah, I mean,
Anybody?
there's a cool notebook. It's a Penny Lane notebook, and it's using the QSIM simulator. Now, the QSIM simulator, they coined this. It was the simulator that went head to head with quantum supremacy, the real hardware. And this is back in the October 2019 Google Nature paper. And you can do this demo and you're cut down on qubits because the QSIM on that case was running on a supercomputer, and your QSIM right now is running on like 90 core Xeon, like a single processor, which is still pretty good compared to other things. So anyways, you get cut down on qubits, and then I can't follow all of it, but it's basically using this transpiled language like the square root of X and square root of S for these gates that you'll see, transpiled. And then it seems pretty cool because it's like I have a somewhat of a similar simulator compared to the one against quantum supremacy. Now, the two things with that is, yes, the quantum computer may have been faster, but as far as error and noise, you'll see things reported in terms of percent accuracy. So typically, you'll like a greater than 70% accuracy for the quantum model is deemed okay. And then your simulator is always going to be a lot less noise and probably better, whatever the results are. But then the quantum computer had the better speed. So it's still a relevant experiment, to do. Like I said, that if I find that notebook, I could put it up. Anybody else that we haven't heard from? Saw a couple people kind of sign on here. Edwin or Shrikanthan?
Kevin, I have a question.
Yeah, go ahead.
So I'm familiar with neural nets and how they work. Basic ideas anyway. So when you do quantum machine learning, you're once again making adjustments based on either some supervised learning situation or unsupervised. And the adjustments you're making are to the rotations of qubits, the degree of rotations of qubits. What benefit is that supposedly compared with classical neural nets?
So it's not as developed as neural nets. I'll give you an example. I had what transfer learning is? It's basically learning from a pre-trained data set. This is all classical. Are you familiar with this?
I mean, it sounds like no, but go ahead.
And in this case, the weights and the biases, the biggest thing going on is either the simulator, it'll take too long, or we don't have the RAM to run, say, like 200 qubits, like especially like a state vector, like a normal circuit. Right. So the deep learning neural nets like ResNet or transformers, these are all well established, and they're running natively on classical code. So they're basically optimal. You could run a GPU with it too. And they're, say for instance, a quantum circuit is going to be smaller just because of the speed of the simulator. So to get those benefits, say like a CNN or convolutional neural network with all of these, like, the deep layered, it's just a much more complex model on the classical end than running like I got up to like 17 or 20 qubits on an abbreviated quantum algorithm. So yeah, it's hard to get that awesome quantum benefit. So say if you want entanglement capacity, so a lot of C0 gates, that really chews up the RAM and barren plateaus, those types of things. So yeah, that's the main limitation is the model itself the classical algorithm inside the hybrid model can't get as big to make a huge difference. So I have this transfer learning model I have is cool because it shuts off the neural network, the classical neural network from updating itself. And then the quantum algorithm, I can compare the two models because the quantum algorithm has the circuit and the classical model also does not update the parameters. And then it's not a big of a change if I can add the neural network, the classical neural network, those hyperparameters, and that's a bigger difference in performance because of this whole circuit size and not using what you ultimately want to use in a quantum algorithm.
I have to confess, I really don't understand. Let me tell you what I think I heard, and you tell me why I'm wrong, because I believe that I am wrong. So when you're dealing with qubits, fewer qubits, I mean, the amount of information that you can deal with in a certain number of qubits is exponential, and that's not true when you're dealing with bits. So you've got 3 qubits and you've got essentially 8 different values represented if they're in equal superposition. Now, is that the kind of size advantage that we're talking about when we're talking about quantum neural nets? That neural nets don't have to be as large if we're working with qubit rotations instead of weights and biases?
Yeah, a lot of it is problem specific. So say if you have an image classification, the variational part of the circuit isn't as important as the embedding layer, which typically does not have C0 gates or entanglement or as much entanglement. So it's really application specific. So, going all the way up to like a Shor's algorithm, just these perfectly tuned, lots of entanglement and these types of things is when you start to have lots of data, like medical data, other things too, that whole model is really slowed down. So yes, I mean, what you said is all right. Like sometimes you want, say if it's a 3-qubit circuit, a certain amount of entanglement, say if like an IBM, what would that be? Like a real amplitudes, something like that, like lots of entanglement. That's just it. There's mathematical advantages to running just single gates. So problems with like H's and rotational gates and X's and Y's and these types of things. There's many cases where your RAM and your runtime go up exponentially as you're adding more things to the circuit. So that's where you have to be careful, and it'll tell you because it'll say the CUDA or whatever is out of RAM. The GPU can't handle this. So yeah, it's a lot of that type of stuff. Like in theory, this would be best for the model. And then you want to look for things that you can do today on limited simulators or even QPUs that, will get you to a decent solution. But I did one of these studies and I watched all these lectures and they say like, if you have global measurement, that goes way up in, runtime, say. And then, certain types of gates, C-knots or Toffoli's, especially Toffoli's and Fredkin gates, those go way up in runtime and RAM. So yeah, if you have that kind of understanding, like what you're kind of running, how much data surrounding it, like going into it, you can kind of get a feel for an appropriate circuit to run that would have some quantum utility to it.
Yeah, if I could add something to Barry's dilemma there, or it seems to me like most of the quantum algorithms that actually have some meat on the bone, they can all be traced back to the phase kickback trick. I mean, you could follow that all the way up to Shor's algorithm, where they're basically tracking the phase of each state also. to, it's basically another dimension. You're encoding data, but specifically with neural nets and quantum, for example, if you have 8 qubits, in theory, you can use those 8 qubits to represent an 8 by 8 digital image that's amplitude encoded. It's only going to be like the slice of an image. It's only going to be 1 bit deep. But now that you have that encoded into the quantum computer, then there's any number of algorithms that you can run that use the phase kickback thing to basically generate interference patterns. And then in the end, the last thing you always have to do is you have to adjust the circuit so that it can be measured in the poly Z state, because that's what most of the people have hardware to do, is measure it in that state. Although there are some simulators that'll let you measure it in any of the states, or any of the poly basis states. But so that's basically it. And again, you'll see where a lot of these things, like especially where the front end to Shores is, all you're doing is it's adding up rotations, and it's adding that rotation information to the amplitude information. So you're getting that super dense coding. As far as getting quantum computers to actually be a slice of your machine learning model, to be a neural net layer, I don't know that it excels at that point, but there are algorithms out there where they can get some either front end work done or some back end work done. And it's based on basically what I've seen. And again, all the algorithms that I've seen recently that have meat on the bone, like the max cut, the random walk, which is both graph problems, traveling salesman, all has to do with playing games with flipping the sign or flipping the phase of a specific set of qubits. I don't know if that helps.
Yeah, I mean, short of quantum algorithm zoo, which is challenging for me to understand, I don't know if there's something where it says like this model. The hardest thing, because the algorithms, like Ron said, like there's a number of that have quantum advantage, and they're proven to be working in all this stuff. But once you put them in models and you have all this data, and there's things working for it, because there was a Google paper generalization from few training data. So they found that in the quantum approach, you needed less data than the classical. So these things come out in literature, and then people, prove or disprove, or, you form opinions on these things. But yeah, there's certain things that you're just doing quantum mechanically that you try to say like, okay, this we could do, and then you can't do it classically for, like I said, like new utility, better performance. And it seems like the last thing that will come is the speed ups, because speed ups, even though the algorithm does it, in a real world case, you have issues in inputs and outputs in a model. So that's a little bit harder to achieve. So Maria Scholl at Xanadu, she always talks about the physics of qubits, understanding those, because when you're passing data through, say if you aren't shooting for speed up, you could still get a different type of processing method in quantum, which people aren't shooting as much for speed, or they're more into speed, or get better performance of the model, right? So the driving force is speed. What we can get, and what people have been getting, according to experts, better performance and utility. So, and everything just depends. It depends on your data set, these types of things. And you have barren plateaus and local minimums, the quantum specific kind of things that can get worse if your qubits get too high, or if you have too much entanglement, error, like that's prevalent in quantum computers, that does not help, in achieving what you want to get to.
Yeah, but I got a question. You're doing this, great. You're using medical information for imaging. So you're building a particular area of a full image in order to basically understand where you're building the whole image?
So it's image analysis. So the images
Right.
already exist.
Right. But you're taking a segment of the image. How much of the image are you actually taking, throwing in?
For the model, like the whole model?
Yeah, for the model.
I don't know exactly. It's based on a Stanford model built up to quantum. They say you can use any high resolution image, so it doesn't
Mhm.
need to get like pre-processed.
Okay, no, I'm just trying to figure out, because I know you mentioned depth, and basically since each image is based upon the fact of the three-dimensionality of that image being layering to actually give you, metadata as opposed to superficial metadata as opposed to important information that basically does. And then if I remember how the image stuff works, then you get interpolation on imaging. The interpolation, once your program figures out all the parameters that would give you the solid data, then it starts to look at that interpolation layer. That kind of, in order to build it and assume that within a certain range that interpolation layer of the information that's partially missing can be interpreted to within a certain accuracy, and then you can trust it because you're looking for that missing piece of information. Does that make sense? Does that make sense?
Yeah, I mean, typically you're just looking at the image itself, so no metadata, nothing like that. And then it's similar. It's basically if you have similar neural networks, classically these models, now you're just adding a quantum circuit in the middle of it. And then at the end of it, or you're taking, say elements, and at the end of it, you take bits again. So those bits go back into classical for other use. Like the final classification of the whole thing.
Kind of related to, say, you're looking at a picture of the sky and you're actually focusing on a Hubble unit, right, of the sky, Hubble parse, and then you're just looking for a black hole. So all the parameters that basically starlight doesn't give you exactly where a black hole might be in position, but it might indicate that something might be there. And then you have to just keep defining those points of reference, those points of reference. Then you can target that once you have the coordinate system set up, target that part of the sky, and you can start focusing on what that image is, how that image is changing based upon the fact that you're now studying coordinate 6057 on the azimuth or right ascension in the sky, and then you can kind of go in and look at same thing. You're kind of looking at there. You look at change each time you see it. That basically can be referenced as a higher accuracy, then that becomes part of the actual image, and then you can build back to that interpolation area because you can speculate on what's out there on both sides, on the medical data or on the sky, and the idea is you're looking for parts that basically are reference, so you can build more and create a theory of what you're looking at. The kind of
Yeah, I mean, a lot of this is just like they're basic models, so no 3D images. It's the most we can get out of it is basically comparing algorithm to algorithm, and then also the benchmarking would be next. But yeah, this is like if you have like a typical ResNet medical image analysis in say like PyTorch, something like that, it's more like that, right? It's just trying to compare the performance of quantum versus classical, in like a conventional way, I guess. Does anybody else have any other questions? So anybody that we haven't heard from, Marcia, Luis, or David Lofi? And I put another thing in the chat. So this is basically, I took a 2014, a 2018, and basically a 2022. And you can clearly see, and especially as you look at the papers, how far the field has gone from 2014. It's, the number of, particularly the number of papers, right? So, and Maria et al., so the other authors too, you know, basically say that we still have to keep going as far as the model, because a lot of these algorithms, even if they have exponential speed up, they still need to, you know, be working in these practical environments. And her big thing, and it makes sense, is to cut back on the speed ups and to say, now we understand the physics of this to get better performance or better utility. Like you can't do it classically, like just classical methods. So yeah, it's a balance between all these things, because if you don't have the hardware and we're stuck at like, you know, they all have a lot of error, you know, so you can keep going up on qubits, but if you compared it to classical, I've heard up to like an Avogadro's number amount of error between the two, and it's probably gotten better since then, but it's still significant. So it's like, you know, if you use this in finance or, you know, people's lives are in line in a car, or medical, you know, medical algorithms for FDA, I with the error, it's going to be hard to fully implement them. So you'll see, you know, especially the IonQ Dell stuff is they're, you know, using what they know about quantum machine learning in a practical environment. But the ion trap quantum computers, I was watching some of the 2023 the Q era, or it's not Q era, it's Q2B 23. So this is QC Ware's big pitch, so you can watch these videos, they're on YouTube. And I you know, they're talking about these applications, you know, with quantum, and they're still relative to running thousands of images and, you know, getting better performance, like your end performance with a quantum computer, it's still a while away with a real QPU. Okay, so anybody else? Okay, so anybody that recently logged on here, so Hilton or Edwin, any updates on running models, algorithms, those types of things?
I haven't run a model yet, but I attended the IBM event that we're trying today and also yesterday, and it was on quantum encryption.
Uh-huh. Are you
And
talking about the summer school?
No, it wasn't the summer school. It was the weekly. It was the weekly meetup by the IBM technical group.
Oh yeah, yeah. So I know
Yeah.
other people attending here. You've seen that too. It's pretty cool. So for instance, it's Fridays at what would this be? It's 9 Pacific or 12 Eastern. So last week there was a nice talk, and then half hour later they had the award ceremony to the Qiskit graduates in school. So that was kind of cool, and a good panel, you know, like discussing where the field's going to go next.
Which one is that one, Kevin?
They should have it up. So, you know, it's the same thing. So it's the Friday talk, you know, and then last week it was a half hour after that, they had a panel of IBM experts. So, you know, they talked a lot about, you know, what's coming up. And one of them does like a ton of research papers. So anyways, they do Qiskit, this whole YouTube or whatever platform of them being on TV, basically, as well as their research, you know, at IBM. Yeah, Qiskit channel on YouTube. So anyways, there's one tomorrow. So that there's, you know, for me, it's 9 o'clock Pacific AM, but for other people, it's 12 Eastern, or if you're in Central in Chicago, it's, I think, what, 11. So yeah, 11. And then
Yeah. I think that the talk yesterday was on quantum safe encryption, and there was this interesting aspect with the speaker saying that some of the algorithms being used today, of course, can be susceptible to being cracked by quantum computers in the future, and so there's this likelihood that some people are storing communications today, like store today and then harvest later. Yeah, and so people are asking, what can we do? But here the speaker was saying that, I'm sorry for anyone who hasn't kind of transitioned to the quantum safe encryption. It's too bad. Yeah,
they call it steal now, decrypt later, basically. And Yeah, I mean, it's the leading field right now, I would say, because they have, so the ISO or IEC, they do regulatory of quantum computing. So the last time I checked, it was past approval, and it was like maybe they're at 60 out of 80. So it's just, that's the scale. And there's two of these quantum standards they're about to pass through. IEEE does a lot with, they already have like 9 or 10 quantum standards, and FDA more relies on like IEC. So IEC will be involved with quantum standards for sure. Trying to think who else, maybe, some things with ASTM, and there's at least one other one, but you kind of get the gist of it. There's a presidential law, or a law signed by the president last December requiring federal agencies to start implementing quantum cyber defense. And the NIST algorithms, correct me if I'm wrong, I don't believe they're actually quantum algorithms. I think they're classical. I don't think you actually need a simulator, but they can defend against quantum, like the best quantum computer attack. So they use the term post-quantum cryptography, which is different from, parameterized quantum circuits. And I think that's the crux of it, is you have to use NIST algorithms to defend. And a lot of companies such as, I think it's, I know Sandbox and others too, or QSecure is another one, they're doing an application of these algorithms. So, if customers or clients know how to implement them on their own, I think they can do that. But there's a whole big industry around utilizing these NIST algorithms once they're fully, passed, to defend against quantum attack. So, but it'll open up a lot of doors because people don't understand quantum, or they're confused about it, or they're scared. And, the whole thing with, having cyber defense against quantum gets people at least knowing what a qubit is, a quantum bit. So it's a good thing for other industries. Okay, so Edwin, so NIST is National Institute of Science and Technology. If somebody, I could put it in the chat here. So basically they have 4 algorithms that are like 99 point whatever % passed. And there's been some updates on some of these potentially not being as robust as they thought. So if I type in NIST quantum algorithms, okay.
I think the speaker was talking about 4 algorithms, but there was some people in the in the talk who pointed out that one had actually been proved not to be quantum safe.
Yeah, and I put in there, so this is probably the biggest update. There's been others. So this is July 22. And then, like I said, since then, there's a law for, federal agencies to start implementing these types of things against cybersecurity attack. You could watch it. I watched some of these NIST ones on YouTube. They're, a little bit older, but you get a gist of what you're talking about, like cybersecurity, quantum computers, these types of things. Barry, did you have something?
Yeah, no, I'm sorry. I just lost something and I'm fiddling around to look for it and I'm making noise. I just wanted to throw in a word that, as far as I've heard also, the post-quantum cryptography algorithms are not themselves quantum algorithms. They're classical algorithms.
Yeah.
Mostly using lattices to.
Lattices.
Yeah.
And aren't some of them a little bit different from one another, like a dicrystal lithium and?
Not actual physical lattices, but lattice theory.
Oh, lattice theory. Okay. Yeah, because I watched one of these YouTubes and it was like, it was a lot earlier than all this, but for this application. And say some of them it was just like some of them just didn't do well at all. Like the teams, the group of researchers using specific ones didn't, and others tended better. So it's interesting.
So quantum computers' ability to generate what people are tagging as truly random numbers, and the business of quantum key distribution, which has been demonstrated and is happening And I believe there's even some companies out there selling that as a service for short haul stuff. These super random and secure keys will go a long way to closing the gap on the quantum, or on the quantum encryption trapdoor, I guess, is, I don't know how else to say it, but there's stuff that's out there that's happening now. So, and it looks like it works just fine.
Yeah, I appreciate you bringing that up because quantum computers by nature are good at noise, probabilistic, random, QK. There's Samsung Galaxy phones. They claim they're quantum phones, but they're really just like quantum random key encryption or quantum random number generator, QRNGs. And yes, as far as like all of this stuff with quantum sensors and quantum security, these types of things, quantum is a very broad field. And then you get into quantum computing, and it's typically associated more with like algorithms and gates or pulse sequences. And that's the stuff that a lot of people are excited about, because especially if the hardware breaks in a good way, then, you get these theoretical exponentially greater processing power and more information, those types of things. So awesome. Was there anybody that didn't have get a chance to talk that have any questions? I'll put in the chat again. So this is I would run a lot of this code at the bottom. So it's basically like how to find which backends are available. Now, a lot of this that we talked about falls under Qiskit Lab. Okay, so Lab is a Python notebook in an online environment, and then you have free access to a bunch of stuff, unless you want like GPUs. And then Composer is where you slide gates into, and then you can print a picture of it and run those directly on a computer. But the lab is the core function where you can do a lot more. So the Composer's limited to certain types of stuff. I think even parameterizing circuits, like it's that you're just running the algorithm on a computer. It's not stuck in a model. It's not being used in a model. So awesome. Any other last questions or comments? So again, you can download the PDF.
Okay, I have a question. Maybe I don't know. When I learned about neural nets, it was way back in the 60s, and at the time, what they were talking about was actual neural nets, not simulations. So it wasn't that neural net was a sort of a concept and you running it on a regular classical computer. It was that they were building these machines, these things. Is there any of that going on now? Do you know, in the classical neural net world? Is there hardware that is neural net, or is it all just simulation of the neural net idea in machine learning? I don't know if you'd know the answer to that or not.
Well, sort of like what comes to mind is an ASIC chip, application specific and whatever. And that's actually running the software, the algorithm, like it's hard coded into the silicon. And I'm not quite familiar with that back then in the 60s, because I know for sure there was an AI winter in the 70s where they had all these great ideas, but just like the computers never came. And all of a sudden, like late 90s, 1990s, now you could start doing deep learning. And I think it really started taking off like 2012, TensorFlow, 2015, even better TensorFlow. But yeah, as far as I know, I think they're all software. That's the first I've heard of that, unless the ASIC chip would count.
Yeah, I don't. Just looking back in history and thinking, I just remember how this was going back.
ASICs were around when I was in electronics from about 1990 back until late 80s, because they started appearing because circuit boards basically were starting to get multi-layer. That was brand new, and they were starting to do surface mount. I worked for a hospitality company, kind of advanced, and they were using that to basically take up circuit board space, or actually it gave more efficiency in circuit space by putting these ASICs.
So what Ron put in the chat might qualify to your question there, Barry.
Mm-hmm.
So he says, I model this, or you can come on, Ron. A small neural, go ahead, Ron.
A couple of years back, I modeled a really tiny neural net using, I didn't build it, I modeled it with electronic SPICE software, circuit simulation software. It's got like 4 or 5 op amps, or I don't know, 4 or 6 op amps in it. And you train the circuit to do a couple of real simple algorithms, and you train it by hand. So you test it, you figure out what you're going to do, and you manually by hand do the back propagation. It's kind of fun to watch, but I understand that back in the day, people that had array of, before digital computers, there were people who played with analog computers, which analog computers are all op amp based. Very easy to build like a multiplier, a very fast multiplier with an op amp, because it does it intrinsically. It doesn't have to time slice it or break it up into pieces or anything like that. But that a lot of it never really caught on. But this area of neural nets, I'm sure there's a lot of work that went on, because you could take one op amp and build a simple model of an actual human neuron just with an op amp and power supply and a bunch of resistors and maybe a few capacitors here and there. But somebody, I think back in the day, actually built an op amp based neural net. I don't know how many op amps it had, but it was approaching the cognitive ability of a cockroach or a
Actually pretty good.
or actually what's the famous one the neurologists study? It's a sea snail of some sort, or a sea slug. There's a creature in the ocean that's only got like 13 neurons, and it survives in the world in the bottom of the sea with 13 neurons.
So the capacitors were used as shielding in order to contain the actual circuit.
Probably mostly to stabilize the power rail.
I'm just saying, because there's a shielding around each nerve that basically carries it through, and then carries it down to the vesicle, or that gets created.
So if you want, if you don't want a discrete neuron, you need some way for the signal to jump from neuron to neuron, and that could have been done with tiny, like little picofarad capacitors. The neuron would fire, and all of the capacitors would transfer a certain amount of that energy to the next neuron over without being directly connected.
There's discharge then, and then the next bar actually.
But you could also build it with discrete synapses, which are just they were just wired together. So.
And you thought capacitors were just for handing somebody that in class and shocking them, right? Never did that.
Never did that. And if anybody says any different,
yeah, I did that once, and someone did it to me, and I had fun.
Yeah, I mean, so there is a lot of literature right now with the whole, so neural nets have like linear and nonlinear components to them. So there's thought that you could use quantum for part of this, right? So it's a really specific thing as far as the application, because we've not even touched the surface of this, because just a PQC, a parameterized quantum circuit, is it's still relatively a basic thing, and it's just because the simulators, we can't go higher, and the real computers have noise. But yeah, there's some experts on this for sure. I'd say Aram Haro, Seth Lloyd. There's many people. Chris Temmie, he works at IBM. D-log function. So D-log function, it sounds like it's a huge thing. I hear IBM talking about it's just then a log. As far as having this exponential speed up for certain applications. But yeah, I mean, there's a lot of research that's been done, but I think a lot of it we'll still see, especially okay, this is exactly how to use quantum, and we can customize everything right now, but now we have a better understanding, and then just do this thing. So it's the same thing. I think we're a little bit like Seth Lloyd. He says QRAM comes first, and then a fault-tolerant quantum computer. And I think on the software side, maybe even before QRAM, these things become, readily available, easy to use.
Well, that
Awesome.
way you don't need RAM.
What was that?
That way you don't need RAM. Process it in the program.
Yeah, some of
And
the algorithms in these paper don't require them. You're correct. So it just depends on the algorithm.
some research.
Yeah. But from the sounds of it, QRAM would help a lot of things out. And so for those that don't know, QRAM is quantum RAM, and then we might only have like a couple seconds. I saw networking in Harvard, say like 6 months ago. And of course, in RAM, we're talking, like not forever, but like, classical RAM, you can store, I think, as long as you want to.
Yeah, and RAM is one of those unfortunate words in quantum. It's not RAM like RAM. It's basically a place where you can park a qubit for a certain amount of time. It's not like you can write quantum state to a location and read it back a bunch of times, obviously. But
Right.
why they chose the word, why they chose the word RAM, I guess it's just to pile on the list of bad words they chose. One last comment about QML, and I'm sure everybody already knows it, is everything that's going on out there is highly hybrid right now. It's like quantum is doing a piece of it, and as time goes on, quantum will get bigger and better, and the work will hopefully render more precise results over time. So
Awesome. Any other last questions or comments? Another good paper is the big table of quantum artificial intelligence. So that one's a weird one because it's like on a web page, but then you click the link and it just downloads it. So make sure to find the link to it. And since I think the early 90s up until now, the different combinations of quantum and classical data and algorithms. So it's going to be it's harder. It's basically raw papers. So awesome. With that, I appreciate everybody coming. This has been discussion 94 for how to create, optimize, and implement quantum ML algorithms, August 3rd, 2023. I'm Kevin Kawchak. So prepare next week, probably advanced stuff. So more into transpiling and pulse sequences. So that's probably what that's going to be like. I wish everybody a good rest of the day. Have a good productive rest of the week. Take care, everybody.